Now, since we want to change the amount of water in the glass or in the path of light, let's see what it does. We have two options here based on our question. Which one refracts more? Does more water cause more refraction? Does less water cause less refraction? From our common sense, we can already have some ideas here. Take for instance, you are told that water can refract light that's coming from air, for example. If water, from common sense, if water can already refract light, then I'm sure that the more water there will be, then I expect more refraction. So if water can refract light, then larger quantities of water will also enable large amount of refraction. In lay terms, it will enable large bending, more bending of the light. So I have two scenarios here, A and B. In A here, I have a glass of water. You see the distance that light travels through as it passes through the water. The distance is from here to here. I'm sure this distance is longer than what we see in B here, where the light will have to pass from here to here. This distance is shorter. So I'm sure in the road, in the path of the light, where does the light pass through more water? Our answer is A. And since the light is passing through more water here, to go back to air, we are leaving from air, water, air. Since light is passing through more water, I'm sure we'll have more refraction, more bending. And here again, air, water, air. Since light is passing through less water, I'm sure refraction also will be less bending. So the more water, the more bending. The less water, the less bending. More, less, more, less. Let's remember that. More, less. We shall then look at two types of lenses. We'll have what we call a convex lens, which is more rounded. You see that. And a concave lens, which is kind of flat. Our concave lens, we can either draw it this way or this way. You'll see that. Let's use this one here. This is the one I'll be using mostly. You'll see that my concave lens here is kind of flattened. It is stretched compared. This one is stretched compared to this one, which is more rounded. So I'm starting to link up the lens of the eye now with amount of water. It means more water, that is it, which causes more refraction. My more water is the same as more convex. Why? Because when I'm passing through the lenses, the one that will present more water in the path of light. Remember again, my more water, this distance is more here, it's more water. My convex lens also, as light is passing through, it will also present more water in the road of light, in the path of light. Meanwhile, my concave lens, as light passes through, it will present less water in the path of light. So which one will cause more bending? Obviously, the convex lens will cause more bending. That's why we have more bending caused by the convex lens, and the concave lens will cause less bending and less refraction. So I've now moved the whole story from our water to the different types of lenses. By now, we should be comfortable enough to understand that a convex lens, because it presents more water in the path of light, will cause more refraction, more bending. We should also be comfortable enough to realize by now that a concave lens, because it presents less water in the path of light, it will also cause less bending. Okay, let me make that a bit more different. It will cause less bending of light. So that's what will happen with the lenses. It means that I have two cases here: more bending, less bending. What do I link it to? I also have two cases for objects that I'm viewing. It's either they are far or they are near. So for which one do I require what kind of lens? Do I require convex lens for near object and concave for far object, or vice versa? Do I require more bending for near object or less bending for far object, or vice versa? Let's see what we need. Before we can conclude on which lens we need for which distance, near or far, let's first see how the shape of the lens is being altered, so we can then put everything together. Now, remember, I'll take this eye here. Remember, we said we have three places where we have water here. We have water in the aqueous humor, in the lens, in the vitreous humor. We can't change these two, but we can alter the shape of the lens such that we have water being presented either less in the path of light or more in the path of light. That's the way. Notice here that we are not even taking out water from the lens to make it less water, or filling it in the lens to make it more water. No. All what we are doing is we are either stretching or letting loose the lens. If we stretch it, it will become kind of long and slender and flatter, with less water being presented in the path of light. If we let it loose, it will become more rounded, with more water presented in the path of light, typical of what we see with convex lenses this side and concave lenses this side. So the question is, we have two scenarios. The lens can either be stretched or flat, or it can be more rounded. The question is, how do we get there? How do we get to a more rounded lens? How do we get to a more flat lens? Before we can now see which lens will be used for either near vision or far vision. We have two lenses here. We need to understand how we get to each, and later on we need to understand now which one will fit which kind of vision. Okay, now for the lens, I'll start with A here. For the lens to be bulged, dome shape, or more rounded, I would like to draw our attention to the ciliary muscles that are found here and the suspensory ligaments. Notice that the suspensory ligaments are attached to the ciliary muscles, or otherwise the ciliary body, and the suspensory ligaments are also attached to the lens. That's what we have here. This is our ciliary body. So what you have there, made up of ciliary muscles being attached by the suspensory ligaments. both sides, and the suspensory ligaments also attach the lens. So then, for the lens to be dome shape or to be more rounded, it means that somehow it needs to be set loose, it needs to be set free. For that to happen, the ciliary muscles must contract. You will see here, they will contract and assume that kind of dome shape. They will swell. You'll see that the ciliary muscles here are more swollen than here. They'll swell up, and when they swell up, what happens? They cause the suspensory ligaments to slacken. You'll see that my suspensory ligaments here in this diagram here are somehow slack like that. Okay, and when the suspensory ligaments slacken, the tension on the lens is released. The lens is set free such that it can be able to bulge out. Imagine you are having a balloon, you've already blown it. When you pull that balloon with your two hands apart, it stretches. That balloon will have more tension. But when you let your hands relax, the balloon comes back into a more rounded shape with less tension. That's exactly what's happening in this case here. My balloon has been released. My hands have been relaxed such that the balloon comes back into a dome shape or a more rounded shape. And in that case, my balloon or my lens has become more convex. I'm sure we can see that. And remember, convex has more water in the path of light. Looking at the concave lens in case B here, what happens? For me to have my lens stretched here, the ciliary muscles here will then have to relax. And the moment they relax, they become more flattened, such that they will pull on the suspensory ligaments, which will also pull on the lens, because the suspensory ligaments have become more tense or taut or tight. That's what's happening down here. The suspensory ligaments have become more tight. Compare the suspensory ligaments with the ones we had here. You will see that here at A, they were kind of very just relaxed. Okay, the suspensory ligaments were less tense. But in this case here, they are tense, they are taut, such that the lens will be pulled on, and this is what gives the lens this more stretched appearance. My lens here is more stretched than the lens we had here. And this stretch appearance is what we'll then refer to as concave, sorry. It's what we'll refer to as concave. So our question of how do we get there? I'm sure by now we've answered how we get to a convex lens and to a concave lens. The role players here are simply the ciliary muscles and the suspensory ligaments. Action, reaction, reaction. Action, reaction, reaction. Okay, that's what happens. Now, this is how the shape of the lens is then altered, such that we have two cases, A, convex, and B, concave. So which one will be for far object, which one will be for near object? We shall see that in the next slide.